welcome to the 7th lecture in this video lecture series. In this lecture 2, we will be continuing our discussion with process scheduling. In the last lecture, we saw one of the process scheduling techniques called first come first serve, and we found that it's a very simple scheduling algorithm to implement. It just needs a queue, and the processes are scheduled according to their arrival time. But the disadvantage of this algorithm was that it depends on the order of the process. So if you change the arrival order of the process, then the overall waiting time of the process of the set of process has an ill effect on that. And we also saw one of the major problems related to this ordering, which we call the convoy effect. That is, if you order the process in such a way that the process with the highest execution time is scheduled first, and then the processes with the lower execution time or burst time, you find that the overall waiting time of the process is too high as compared to the situation where the processes with smaller burst time, they were executed first, followed by the process with the longer burst time. So the convoy effect of the FCFS algorithm was some kind of an indication that if you schedule processes with a slower burst, with a smaller burst time first, that will be better as compared to scheduling processes with the longer burst time. And this argument should lead us to the fact that FCFS was scheduling processes on the basis of arrival time. However, a better parameter to decide on the scheduling is not arrival time, but a better parameter to decide is burst time. So based on that argument, the next algorithm that we are going to talk about is called shortest job first, and the name itself should trigger you that it's the decision to be taken based on the burst time of a particular job or a process. It's not the arrival time that is important here, and that is why we call this algorithm as SJF. Okay. Now this particular shortest job first algorithm has two variants. One is the non-preemptive, which is the one that I will be starting off with. Non-preemptive means that if a particular process has started execution, we do not stop that process in between. Okay. What I mean is, if there are a set of processes, and looking at that process, you have decided that okay, there is a particular process which is having minimum burst time, and the process you allocate to the CPU and the process starts. Now after some time, as the process was executing, there is some other process which came into the ready queue, and that has a burst time smaller than the one which is being currently executed. If that is the situation, then there is a decision to be taken. Should you stop the process that is in execution and allow the newly arrived process, or should you continue with the process which is in execution until it finishes, and then you take the newly arrived process and allocate it to the CPU? So these are the two ways of deciding. The first one, where you allow a particular executing process to go on even if the newly arrived process has come with a burst time smaller than the one that is currently executing. So you do not stop the currently executing process. We call that as a non-preemptive. You do not stop it. Preemption means you stop that in between. So we don't stop that particular process in between. You allow it to continue. And then once the process terminates, then you can check the ready queue and find out the process which has the smaller burst. The other one is the preemptive form of this SJF, where if a new process arrives with a burst time smaller than the process which is running on your CPU, then you stop the process that is currently in execution and you allow the newly arrived process to be executed. This is called the preemptive version. The preemptive version of this shortest job first is called shortest remaining time first algorithm. We'll look at that later on. So first let's start off with the non-preemptive version. Non-preemptive means we will not stop the process that is currently in execution even if a new process arrives with a burst time smaller than the executing process. So in order to understand this further, let's take a numerical example and say we have a certain number of processes and the arrival time of them is provided as follows. We have 4 processes, say P1, P2, P3 and P4, and the arrival time are 0, 2, 4 and 5, and here we have 7, 4, 1, 4. So if these are these processes that we have. Let's try to schedule this, and at the same time we will also draw the ready queue. This is our Gantt chart, and this is our ready queue. Let's keep this open because we may need to extend. So we'll start with first the shortest job first, okay? But we will start with time instant t equal to 0. So at time instant t equal to 0, there's only one process, P1. Okay. So P1 arrives, it doesn't have to sit in the ready queue because there's no other process, and the scheduler immediately picks up the process and it allocates it to the CPU. So P1 starts executing. Okay. And P1 starts execution. Let's see what happens at time instant t equal to 2. Because at time instant t equal to 2, a process called P2 arrives. And P2 has a burst time of 4, which is less than the currently executing process P1, which has a burst time of 7. But even if P2, which arrives with a burst time lesser than the currently executing process, we decided that we will not stop process P1 and let process P1 continue because it is non-preemptive. So P1 should continue. So what should be done to P2? Obviously P2 should come and wait in the queue. So P2 comes and waits in the queue. P1 continues. P1, let's look at the instant when at time t equal to 4, because there's something that happens at time t equal to 4. At time t equal to 4, there's one more process that comes in, which is called P3, which has a burst time smaller than either of these two. Definitely smaller than the one that is currently going on. But we will not stop P1, we decided that. So where will P3 sit? P3 will also sit in the ready queue. So now we have 2 processes which is sitting in the ready queue. Okay, so once we reach time instant t equal to 7, which means we are done with P1. Okay. Now it's the time of the scheduler to come in, because we said that scheduler schedules once an event, one of the events where a process terminates may occur. So process terminates here. Now the scheduler looks at the ready queue and it finds that only P2 and P3 are the 2 processes. It compares these two, the burst time of both of them, and finds P3 to be having a smaller burst, which automatically means that P3 at time instant t equal to 7 is taken out of this. So now P3 is taken out and now it is allocated. So P3 starts executing. Okay. Oh, by the way, I missed that. At time instant t equal to 5, I should have. At time instant t equal to 5, we have one more process that arrives, which is P4. So at time instant t equal to 5, the status of the ready queue is P2, P3 and P4. So obviously when P3 has been allocated, we have P2 and P4 which is lying. So there's no point in choosing, there's no problem in choosing P3 because P3 has the smallest of the burst time among P2, P3 and P4. So when the scheduler takes a decision at time instant t equal to 7, it gets P3 to be the minimum and it allocates. Okay, and right, so P3 is allowed to execute. P3 executes for 1 unit of time, that is at t equal to 8, it finishes its execution. Once it finishes the execution, again it's time for the scheduler to look up the queue and it finds there are 2 processes, P2 and P4. It looks up to the burst time of both of them and finds that both of them have the same burst time. So that's a time. In case of a time, you can choose any one of them. Let's assume that we will be going with P2. So say the process P2 now is taken out of the queue and it is allocated. So P2 executes for 4 units of time, that is at t equal to 12, it finishes off its execution. Once it finishes, again the scheduler looks up to the queue and finds that there is only P4 which is there, so it allocates P4 and P4 executes for 4 more units of time, that is at t equal to 16, it completes its execution. Okay, so once all of them have completed, now let's try to fill up this and see what happens to the waiting time. But first, let's compute the completion time. Okay. So what is the completion time for P1? The completion time for P1 is 7. Completion time of P2 is 12. Completion time of P3 is 8. And completion time of P4 is 16. Right? Okay, so if the completion time has been computed, let's compute turnaround time, which is CT minus 80, which means it's 7, it's 10, and we have 4, and we have 11. Okay, when T80 has been computed, let's compute waiting time. Waiting time is turnaround time minus burst time. So 7 minus 7, it is 0, 10 minus 4 is 6, 4 minus 1 is 3, and 11 minus 4 is 7. So 0, 6, 3, 7, that's what it comes out to be. So let's compute the waiting time, the average value of that, and it is 0 plus 6 plus 3 plus 7 by 4, and that's 4. Okay. So you have the average value to be 4. So this is how we schedule processes which are on the basis of non-preemptive shortest job first. Okay. So let's write this down, that if it is a non-preemptive, then we have the waiting time of the average waiting time, it came out to be 4. Right. Now let's talk about the preemptive version and see how that works. So let's remove this. Okay. So we have now the preemptive SJF. Now once we talk about the preemptive SJF, we should be careful that now we have to take out processes from the execution state and allow a process with a lower burst time to get executed in case it has a burst time smaller than the one that is currently in execution. So now let's try to do the same thing, but this time remember it's a preemptive SJF. Okay, so let's draw the Gantt chart again and we'll look at the ready queue. So this is the ready queue and this is the Gantt chart. So at time t equal to 0, there's only one process P1 which arrives. So process P1 arrives and immediately gets a chance to be executed on the CPU. Okay, so till a new process arrives, we don't have to worry about anything. P1 continues. Now, when at time t equal to 2, we have a new process that arrives, which is P2. And now we have to be careful because the scheduler now has to do some additional job. It first has to look up this process called P2 and find out what is the burst time of the newly arrived process. It finds it is 4. So the burst time of P2, okay, is less than the burst time of P1, which means that P2 should be scheduled. So this is the decision that the scheduler arrives at, that P2 should be scheduled. Okay, so P2 should be scheduled. Fine then. So P2 should start. But if you schedule P2, that means that you allocate P2. What will be happening to P1? P1 must be taken out, and P1 must be now put into the ready queue. Now P1 will go and sit in the ready queue, and P2 will start execution. Now something more has to be done. What? We have to update this burst time of P1 because P1 has already executed 2 units of its execution time. It says it has completed its 2 executions. So it has 5 more units of time to go. So you have to update the burst time. So this is the new burst time of P1, which will be following this. Okay, so now P2 starts execution. P2 executes for 2 units of time until we have a new process that arrives called P3. And P3 arrives at time instant t equal to 4. So P2 by this time has completed 2 units of time. Let's see. So now our scheduling decision has to be taken at t equal to 4 because at t equal to 4 we have another process called P3 and it has come with a burst time of 1. Now look at the decision to be taken. There is a newly arrived process P3, a process which is currently executing with a burst time 2 units of time because 2 has already elapsed, and a process which is sitting in the ready queue with a process with an execution time of 5. So the comparison between 5, 2 and 1. And what you find is that this newly arrived process called P3 should be allowed to execute next because it has the smallest burst time. So you allow P3 to get executed. Because P3 has to be executed, you have to take out P2 and P2 now must go and sit in the queue along with P1. Okay. Again, P3 continues until t equal to 5. So at t equal to 5, because it has only 1 unit of time, it's exhausted that, and P3 ends at time t equal to 5. And at the same time, at time t equal to 5, there's a process that arrives which is called P4. Now there's an interesting thing that happens. Because P3 has terminated, now again the scheduler has to take a decision which of the processes should be scheduled next. It should be among already existing 2 processes in the queue, which is P1 and P2, and the process which has just arrived called P4. So it will look up to the remaining burst time of the P1 and P2, which is 5 and 2, and the one which has arrived, which is 4. And it finds that P2 should be given a chance because P2 has a remaining burst time of 2. So it picks up P2 and it removes it from here. So P1 and P2 gets removed, and the newly arrived process called P4 now comes and sits in this. Okay. And P2 continues. P2 continues until 2 more units of time, that is at t equal to 7. At t equal to 7, it completes its termination. And once it completes termination, again the scheduler comes in the picture and it has to schedule the next process. And it finds that there are 2 processes which are sitting in the ready queue, P1 and P4. So now it has to compare between P1 and P4 and finds that P4 has a smaller burst time. So obviously it removes out of P1 and P4, it removes P4 from here, it allocates that, and P4 continues for 4 more units of time. Okay. So P4 continues for 4 more units of time, that is at t equal to 11, you have P4 completing its execution. Once P4 is done, then the only process left is P1, and P1 will now be given a chance to be executed, which executes for the remaining of its 5 units of time, and that is at t equal to 16, it finishes of its execution. So this is what happens if you have a preemptive shortest job first. So this preemptive form of shortest job first is also called shortest remaining time first, because you are actually comparing to the burst time in this case. Right? So whenever a new process arrives, a scheduling decision has to be taken. Either the new process arrives or you have a process terminating. So when a process terminates, it's just a lookup to that particular queue and pick up the one with the minimum burst time. But when a new process arrives, then there's a check to be made whether the new process has a burst time smaller than the one that is already in the ready queue or in execute queue. Actually in the ready queue, because the process in the ready queue should not have a burst time smaller than the one which is executing. That is the reason why they are in the ready queue. So the check is actually made between the newly arrived process and the one which is in execution. So once we have done that, let's complete the completion. Let's fill up this column. So completion time of P1 is 16. Let's then bring them to the original burst time because we are going to compute. Okay, so completion time of P1 is 16. Completion time of P2 completes at 7. P3 completes at 5. And P4 completes at 11. So that is what we have, the timing instance. Turnaround time is completion time minus arrival time. So 16 minus 0, which is 16. 7 minus 2 is 5. 5 minus 4 is 1. And 11 minus 5 is 6. Waiting time is turnaround time minus burst time. So 16 minus 7 is 9. 5 minus 4 is 1. 1 minus 1 is 0. And 6 minus 4 is 2. That's what we have. So now if we calculate the waiting time, the average of these, you have 9 plus 1 plus 0 plus 2 by 4, and that comes out to be 10 plus 2, 12, this is 3. So look at this. The preemptive, for the same set of processes, the average waiting time was, now it's reduced to 3. Okay, so clearly you see having a preemptive form of the shortest job first schedule or the shortest remaining time first schedule. The preemptive form of that clearly has an advantage because it has a lower waiting time as compared to the non-preemptive version. Okay. So the first advantage that we had is our shortest job first algorithm considers the burst time as the criteria for scheduling and not the arrival time. And the second advantage is if you try to impose a further restriction on the scheduling criteria, that will be scheduling based on the comparison with the, if we compare with the newly alive process, the burst time of that with the executing one, and we stop the executing process, so in that case you have a further improvement, that you have a minimum waiting time compared to the non-preemptive. So this is about the shortest job first algorithm. But this particular algorithm, both the variants of that, the problem that should be asked is, okay, we are talking about processes. We are talking about scheduling of processes on the basis of burst time. But how do you compute burst time? So that's a problem that should be, asked. That how do we compute burst time? Yes, this is a very pertinent question because once you execute a process, only then you get the burst time. So how did you get all these values of burst time before? Okay, so the answer is we don't get the burst time, we predict burst time. That's the only way to do it. Predict the burst length. You don't predict the entire burst duration, you predict what is the next burst length of a particular process. And how do you do that? Okay, there are two ways of doing it. One is called the static and the other is the dynamic. The static is where you decide on a certain burst length based on the size and the type of a process. Now, by size I mean if there's a certain process, say P, which is taking some 100 kilobytes of space in memory, And there is another process called P dash, which is also taking say 100 kilobytes or maybe 105 kilobytes. It's the same order of space. Then you may say that, okay, if since both of them are of the same nature, if P takes 2 milliseconds to compute, okay, if the burst length is 2 milliseconds, perhaps this fellow will also be taking 2 milliseconds. So that's kind of a prediction that you do, okay, depending on the size. The other thing could be that you look at the process type, okay, whether it is a computational intensive process, whether it is a compute intensive, or it is IO intensive. IO intensive processes obviously will be having lesser CPU burst because they spend most of their time in accessing IO and they spend very small amount of time in CPU. So there will be smaller CPU burst for this kind of processes, and there will be larger CPU burst for CPU intensive. So you can clearly have two groups of process. So looking at a particular process, you can distinguish between whether it should be in group compute intensive or should be in IO intensive. Accordingly, you can allocate, okay, maybe compute intensive tasks are taking say 50 milliseconds, whereas this is taking 5 milliseconds. So if there's a particular process P, I first have to decide whether it falls in this category or this category. If it falls in this category, then automatically I give it 5 milliseconds. That's another way of predicting. But you see, in both cases, whether you are deciding on basis of size or you are deciding basis on the type, that's an inaccurate way of doing things. And that is the reason why this kind of prediction, they often result in erroneous scheduling. If you go with erroneous burst values allocated. It is better to have a dynamic approach. And in dynamic approach, we again have two kinds of, what is this dynamic approach? That means you decide on the next burst length depending on what is going on now. What do you mean by that? You come up with some mathematical relation or some mathematical model, and based on that you decide what should be the next burst length. Say for example, if there are say n number of processes, pi for I equal to 1 to, so there are n number of processes where you have I equal to say 1 to n, okay, and you want to calculate the burst of pi plus 1, the next burst of pi plus 1. One option would be that you compute the burst lengths of all ti, that is for I equal to 0 to n, 1 to n, and then you divided that by n. So you simply take an average of all the compute times of the processes that you know. So you know already the burst time of say n processes, and there is a process, unknown process called pi plus 1. If you would like to predict its burst, you simply take the average of all the burst time of the known processes, and you call that that's the burst time of the I plus 1th process. That can be one option. The other option can be an exponential average. So this was a simple average, and the other option could be you rely on exponential average. That is, you don't look at the burst time of the other processes. Rather, what you do is you look at the the computation of the process till a certain instant of time, and then you decide on the next burst based on the information obtained about the burst till a certain instant. What I mean is, if you're talking about, let's say, what is the n plus 1th burst length of a certain process, let's call that tau n plus 1. So what we can do is, we can decide on, say, something like alpha tn plus 1 minus alpha tau n, where tau n is the predicted burst length. Okay. This is the predicted burst length for the nth cycle or nth burst, and Tn is the actual burst length for the nth burst, and this is how you are going to predict the n plus 1th burst length. So what you take into account is both the things, the predicted value of the nth burst as well as the actual value of the nth burst, and you take this alpha as a weighted factor. We often call this alpha as a smoothing factor. or a weight in this case, and it lies between 0 to 1. So you see, if you have alpha equal to 0, which actually means if alpha is equal to 0, so in that case you have tau n plus 1 becomes equal to tau n. Okay, alpha 0 means you are not interested in the actual values. Whatever was predicted till nth value, you continue with that in the n plus 1. Whereas if you have alpha equal to 1, if you substitute alpha equal to 1, you get this factor to be 0 and this will be Tn. So tau n plus 1 in that case is Tn, which means now you are looking at the actual value, that is the history of that. And based on that, you are deciding what should be the next burst length. Okay. So these are the different ways in which we can predict the burst length. It's true, we don't have any option to compute burst length, but we can predict. And this is the basis of burst values that have been used or are used in case of the shortest job first algorithm. Okay, so now with this idea, let's look at another very interesting algorithm, and we call that as the round robin algorithm. Okay, so what is this? So far we were making our decisions based on either the arrival time or the burst time. Now we'll have an algorithm which will be a fair algorithm. Okay, that is, we don't want any process to starve. What do we mean by that? We mean there can be a possibility when a particular process is being given undue advantage, whereas another process is never getting a chance to be executed. There is a problem. There is a possibility in case of shortest job first algorithm, where you may find that you are working with processes that are currently running in your system, and we decided that okay, a process with a lesser burst time will always be given a chance. Now suppose there's a process which has come, a process which has arrived and has a burst time quite higher as compared to other processes. And so that process will be scheduled later. Now you have processes which are having lower burst time that are currently being executed. And think about a situation when constantly processes are coming with burst time smaller than the one that we had scheduled later on. So in that case, the process with a higher burst time will never get a chance, because constantly processes are coming with a lower burst time, and that particular process is never getting a chance to be executed. That can lead to the process with a higher burst time to starve. We don't want this kind of situations to occur. So why can't we have a more fair scheduling? And one of that schedule that we are going to talk about now is called a round robin schedule. Round robin schedule is a technique where you have processes. Every process is allocated a time slice, and the moment that particular time slice expires for the process, even if the process has not completed its execution, it will be forcibly terminated, not terminated, it will be forcibly preempted and will be taken out of the running state and put in the ready state. So it's this that we had discussed earlier, that if a process which is currently in the run state, there is a possibility that you may have this transition. When does it happen? It happens if the timer elapses. So there's a timer which is associated with every process. When it elapses, it is taken and put in the ready queue. So this is the basic idea of a round robin schedule, that we have a look at the execution of the round robin scheduling policy with a numerical example. Consider 4 processes P1, P2, P3, P4 and their arrival and burst time as given here. And let's consider the time slice associated with every process be of 2 time units. Okay, that means after every 2 units of time, a currently executing process, if it does not finishes its execution, will be preempted and will be put back in the ready queue, and some other process from the ready queue will be given a chance to get executed. Let's see what happens through the Gantt chart, and at the same time we will also look at the ready queue, because this will help us visualize better. So this is the ready queue and this is our Gantt chart. Okay, so let's begin by scheduling the processes starting from time instant t equal to 0. At time t equal to 0, the only process to arrive is process P1. So process P1 arrives. It does not have to remain in the ready queue because it's the only process there, and it immediately gets a chance to be executed. It executes till time instant t equal to 2, and at time t equal to 2 there is one more process that arrives, that is P2, and because the process P1 has completed its time slice and has not completed its execution, 5 more time units of P1 is yet to go, so it should be taken out of execution and put back in the ready queue. So we put back P1 in the ready queue and we allow P2 to start execution. P2 starts execution and it is allowed 2 more time units. So P2 would be executing for 2 more time units, but in the meantime, at time instant t equal to 3, there's a process called P3 that arrives. Okay, so P3 arrives, and because P2 was going on and P2 was executing, P3 should come and sit in the ready queue. So this is the queue that looks like at time t equal to 3. Okay, that is P1 sits at the head of the queue because that was the process which was sitting earlier, and now P3 comes and sits in behind of P1. Okay, so at time t equal to 4, P2 has completed 2 units of its execution but has not completed its entire execution. So it is yet to complete 2 more, but it has elapsed its timer, so it should also be taken out of the queue of the execution and put back in the ready queue. And somebody from this ready queue will be given a chance. Who will be given a chance? P1 will be given a chance because P1 is at the head of the queue. So P1 is allowed to be executed and P3 moves up in the queue and P2 sits behind P3. That's the status at time t equal to 4. So starting from t equal to 4, P1 again gets 2 units of time to be executed. Okay, and let's see if there is some process that arrives in between. No, because there is no process that arrives till t equal to 6. So this is the status of the queue at t equal to 6. At t equal to 6, that is when P1 executes 2 more time units, still it has 3 more time units to go, that is it has not completed its execution. It is taken out of the execution state or the run state and put back in the ready queue. Okay. So if it has to be put back in the ready queue, somebody from this ready queue will be given a chance to get executed. Who is it? It's the one which is sitting at the top, that is P3. So P3 will be given a chance to be executed and P1 will be sitting in the ready queue. So P2 moves up in the queue and P1 sits behind P2. Okay, now P3 starts executing. It takes 2 units of time at t equal to 8, and at t equal to 8, P3 completes its execution. So in any case, whether it is completion of P3 or the expiry of the timer, the scheduler at time t equal to 8 should take a decision whom to be allocated next. Because there is no other process which has come, it has to be between these two, and P2 is at the head of the queue. So P2 will be given a chance. So P2 is given a chance from here. Okay, so at this, P2 is given a chance. P2 executes for 2 more units of time, that is at t equal to 10. For 2 more units of time, P2 completes its execution. And okay, but at time t equal to 9, there was a process P4 that arrived. So P4 arrived at t equal to 9, and P4 comes and sits behind P1, right? So that is how it works. Okay, so at time t equal to 10, we have process P2 that completes its execution, and again the scheduler has to take a decision and has to allocate any one of them. It's P1 that is again given a chance to be executed. So P1 is given a chance at time t equal to 10. So this is taken out and put here. So P1 again executes for 2 units of time, that is at t equal to 12. And even at time t equal to 12, it has not completed its execution because there is one more unit of time to go for P1. So because it expands its timer at 12, the scheduler again decides to take it and put back in the ready queue. So P1 is again put back in the ready queue, and the process which was there in the queue, which is P4, is given a chance to execute. P4 starts execution at time t equal to 12. P4 just takes 1 unit of time. So at time t equal to 13, it completes its execution. When it completes its execution at time t equal to 13, the timer then looks up to the queue and finds that there is only one process P1 that is residing in the ready queue. It takes it and it allocates it. So P1 is allocated, and P1 now requires only 1 unit of time, that is it executes for 1 more unit of time, and at time t equal to 14, it completes its execution. So you see that at time t equal to 14, all processes have completed execution. Now once the schedule is ready, now let's try to look at the parameters that we usually compute, starting with completion time first. So let's fill up the completion time of each process. P1 completes at time t equal to 14. What about P2? P2 completes at this time, that is at time instant t equal to 10. P3 completes at 8, and P4 completes at 13. Okay. Now when completion time is calculated, let's compute turnaround time, and turnaround time is completion time minus arrival time. So this minus this, so 14 minus 0, which is 14, 10 minus 2, which is 8, 8 minus 3, which is 5, and 13 minus 9, which is 4. Now we compute the waiting time, which is turnaround time minus the burst time. 14 minus 7 is 7, 8 minus 4 is 4, 5 minus 2 is 3, and 4 minus 1 is 3. So once the waiting time has been calculated, let's try to find out the average waiting time of all the processes. That comes out to be 7 plus 4 plus 3 plus 3 by 4, and that is 4.25. So it is 4.25. Okay. So this is how we compute the average waiting time for a round robin scheduling policy. Now let's try to compute the response time now. So what is the average response time of all the 4 processes? What is response time? The time duration between the arrival time of a process and the first time that that particular process gets to execute on the CPU. You see, P1 executes a number of times, but what is the first time that the P1 gets to execute on this? At time instant t equal to 0, because it arrived at t0 and immediately it got a chance. So the response time, it did not spend any time in responding, it immediately got its response. So the average response time of P1 was 0. The response time of P1 was 0. What about P2? P2 came at 2 and immediately got a chance. You see, the allocation P2 was allocated at time instant t equal to 2, and P2 came at 2, so it immediately got a chance to get executed on the CPU. So the response time of P2 was also 0. What about P3? P3 was allocated at time t equal to 6, but P3 came at time instant t equal to 3. Okay. So it came at time instant t equal to 3, but got its first chance to be allocated at time instant t equal to 6, which means its response time is 6 minus 3. What about P4? Okay, P4 came at 9, but P4 got its chance at time instant t equal to 12. So P4 has a response time of 12 minus 9, and that sum total of all these 4 by 4, which is 3 plus 3 by 4, and that comes out to be 1.5. So this is the average response time of this round robin schedule. Okay. Now let's try to compute one more parameter for this. What is it? Let's try to compute the number of context switches. What is the number of context switch? The number of times that you have taken out the process and allowed a different process to be executed. What is that? The number of times the switching between the process. That's one. Okay, that's one context switch. Then we have 2, we have 3, 4, 5, 6, and 7. So the number of context switch in this case comes out to be 7. Isn't interesting? Okay, so average response time is 1.5, average waiting time is 4.25, and number of context switch is 7. Okay, now let's try to repeat this whole procedure, but this time we'll allow a time slice, a different time slice, and let's say the time slice is maybe 1. Okay, so you have the time slice as 1. Now with this, you have a very interesting thing that comes up. Okay, what happens is, let's see the Gantt chart, and let's try to compute the waiting time and response time again. So let's schedule it, and so what we have here is, with time slice equal to 1, it means that after every time instant, okay, after every 1 unit of time, you have a process which will be taken out if it has not completed its execution. So we reduce the time slice, and let's see what the situation is in this case. Okay, so we have at time instant t equal to 0, P1 which arrives, so P1 immediately gets a chance to be executed. Okay, but P1 takes only 1 unit of time, that is at time t equal to 1, you take P1 out. Okay, but nobody else has arrived, so you take out P equal to 1, but since there is no other process which has arrived in the ready queue till at time t equal to 1, so you have no option but to allow P1 to continue till time instant t equal to 2. At time instant t equal to 2, you have a process called P2 that arrives. Okay, because P2 arrives and P1 has expired its time unit, P2 should sit in, P2 should be allocated, and P1 should be put back in the queue. Okay, now P2 again, it's only, so by this time it is 5. Okay, and P2 is allocated, P2 executes till time instant t equal to 3. Okay, and at time instant t equal to 3, you have a process called P3 that arrives. So P2 expires, and what is the status of the ready queue now? We have P1 that is setting, P2 should be, sorry, P2 expires, so P2 should be taken out and should be put back here, and at the same time P3 also comes. Okay, so first let's put P2, then we will put the arrival process P3, and because now somebody else should be given a chance. Okay, so it is the one that is residing in the ready queue, which is P1. So P1 again gets a chance, and P1 finishes off this in P1 again executes for 1 more unit of time, that is at t equal to 4, and you see this process continues for the entire time duration of all the 4 processes. Continuing in this way, if we complete the schedule, this is what the schedule looks like for this set of processes with time slice equal to 1. Okay, and using this schedule, we fill up the completion time, turnaround time, and the waiting time. And once we have obtained the waiting time, if we calculate the average waiting time, it comes out to be 7 plus 6 plus 3 plus 1 by 4, and that is again 4.25, which is same as the one obtained with time slice equal to 2. But interestingly, let's try to compute the average response time. And now we have an interesting thing to know. What is average response time of P1? P1 arrived at 0 and immediately got a chance to be allocated to the CPU. So the response time of P1 is 0. Response time of P2? P2 got allocated at time t equal to 2 and arrived at 2. So that means it arrived and immediately got a chance. So its response time is also 0. What about P3? P3 got its first chance to be executed at time instant t equal to 4, whereas P3 arrived at time instant t equal to 3. So the response time of P3 is 4 minus 3, and response time of P4 got a chance to be executed right here, that is at time instant t equal to 10, whereas P4 arrived at time instant 9. So that means the response time is 10 minus 9, that divided by 4, which means we have 1 plus 1 by 4, which is half, and that means it's 0.5. And if you compare the response time of the one that we obtained in case of time slice equal to 3, it was 1.5, right? So the average response time with time slice equal to 2 was 1.5, and here we have 0.5, which means that the processes, they get their response immediately when they come to the ready queue. So the overall response time of this set of processes is reduced if you reduce the time slice. But what is the, nothing comes for free. What is something that we have to pay? Let's look at the context switch. How many context switch we have? Okay, here is 1, because P1 to P2, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and this. So the number of context switch you see is 11. And what was the context switch in this case? The number of context switch was 7. That's the cost that you have to pay. That is, if you reduce the time slice, your context switch will be more. And that is obvious, because now, after every time unit, you are taking out a process and allowing another process to be executed. So that happens at a more faster rate, and that is the reason we have the number of context switch which is increasing. Now, you can take that as an assignment to repeat the same experiment when the time slice is higher than 2. Let's say for time slice equal to 5, what happens? So what we will find is that for time slice which is say something as 5, you will find the number of context switch that decreases. If the previously at time slice equal to 2 it was 7, you will have a reduced number of context switches. It's obvious, because now the time slice is increasing, so you are allowing more processes to execute for a longer time, and that eventually means that more processes will complete their execution within the time slice. So the number of context switching required will be less. So that is what we find, that the time slice that we choose in a round robin schedule has an impact on both the response time of the set of processes as well as on the context switch. So the trade-off is that if you want to have a lesser number of context switch, increase your time slice, and if you have to have a better response time, decrease your time slice. So it depends on what kind of application you are going for, and accordingly whether you want number of context switch to be less, or you want a faster response time, you have to make a choice. The trade-off is depending on the application, and accordingly you will talk about a different scheduling technique called priority scheduling. In this kind of scheduling policy, we associate a priority number to every process. See, for example, in this case we associate an integer called a priority number to different processes. The idea is that this priority number would indicate which process is of higher importance. A priority number with a lesser value, say for example in this case a value 0, means that out of all the processes, process C is of the highest importance, followed by process D and E, and then we have process A and B. Why do we do that? Because processes are of different nature and processes have difference in importance. Some processes are highly important, the real-time task, say for example. If you have to compare the real-time task with the normal task, obviously you will prefer a real-time task to be executed earlier compared to the normal task. So when we perform scheduling, when we decide on scheduling policy, we should also look at the type of an application or type of a process. And there we have to decide whether a particular process is more important than the other. In that case, you give preference to the process with higher importance to be scheduled earlier than the processes of lower importance. And to demarcate that, we associate an integer called a priority number. This priority number, which is associated, it marks the importance of that particular process, and it can be done by the scheduler or it can be done by the user process. So any one of the two can associate this priority number a priori before you start performing the schedule. And for the time being, let us assume that this allocation of the priority number is static. That is, once it has been done, it is fixed for that particular set of process until the schedule is over. So with this, let's begin the priority scheduling. And again, we have two variants of that, whether you have a preemption or a non-preemption. Preemption means if you have allocated a certain process and the process is continuing, suddenly there is a process which comes into the ready queue with a higher priority, but in a non-preemptive technique you don't stop the currently executing process, you allow it to continue until it finishes its execution, and then you allow the lower priority process to begin, the higher priority process to be allocated. It's very similar to shortest job first without preemption. So you can consider shortest job first as a priority based schedule where the burst time is kind of a priority. Okay. And the other variant is the preemptive form, where if a particular process with a higher priority comes and the currently executing process has a priority lower than the newly arrived process, you stop that and you allow the newly arrived process to begin execution. So it's like this. So let us consider A, B, C, D and E, the 5 processes which we have. So let's first look at non-preemptive. At time instant t equal to 0, that is at time instant t equal to 0 here, process A arrives and there is nobody else, so process A continues, and even if that is the lowest of a priority 3, A continues, and it continues till its burst, that is till it completes its burst, which is, let's say, at time instant t equal to 20, and within this time when A was executing, there are processes which have arrived. B has arrived and C has arrived. So if you look at the queue, at time t, you find that B and C are there in the queue. Okay. Now once A is over, now the scheduler looks at the queue and finds that there are 2 processes B and C, and it looks at B and C. The one to look up is the priority number for both of them and finds that C has a priority 0, so obviously it will allow C to get executed. So C now starts execution and it should continue till 20 more time units, so till 40 time units. During the time when C was executing, 2 other processes have come, D and E. So now if you look at the ready queue at time t equal to 40, you find that there are 3 processes which is sitting, B, D and E. So when C completes execution, the scheduler looks up to the ready queue and finds who are the processes which are sitting, B, D and E, and it looks up the priority number of each one of them and finds that D and E have lesser priority compared to B, but there's a tie between D and E, so you can choose with any one of them. Let's go for D. So D is given a chance to get executed. D executes for 50 more units of time, so that is at 55, D completes its execution. So when D completes, again the scheduler looks up to the queue and finds that there is only B and E that is residing in the queue. And again it compares the priority, finds that E has a higher priority, it gives E a chance. E again computes till 20 more units of time, that is at till 75 it completes, and when it completes, it again looks up to the queue and finds that there is only one B which is sitting, so it gives B a chance, and B executes and finishes off its execution at time instant 90. So this is what happens in case of a non-preemptive schedule. Let's do the same thing for a preemptive one. Okay. So for a preemptive schedule, we'll start off with the same thing, that is at time instant t equal to 0, and at time t equal to 0, A starts execution. A executes, and A should execute till 20, but the problem is at time instant 5, that is at time instant t equal to 5, okay, there is a process B which arrives. So process B arrives here. But since process B arrives and has a priority number higher than or lower than, that means higher priority than A, you automatically take A and you allow B to execute and you put A in the ready queue. So this is the status after t equal to 5. So B, by this time A has completed, remember A has completed its 5 units of time, so it's left with 15. So now B starts executing. B should execute for 15 units of time, okay, but the problem is at time t equal to 10, that is at time t equal to 10, there is one more process that has arrived, which is C, and that has a priority lesser than the priority of the currently running process, which is B, which means that B should be stopped at time t equal to 10 and should be put back in the queue along with A, whereas C should be given a chance to execute. So C starts executing, and because it has the lowest priority, C continues till 20 units of time, so this is 10. C continues till 30, but during this time when C was executing, there are two processes D and E which have come. So now if you look at the queue, after t equal to 30, you have A, B, D and E, all are present. Okay, so C by this time is complete at time instant 30, and now we have a choice between A, B, D and E. So because A and B have lesser priority compared to D and E, so obviously D and E, one of them will be given a chance. So let's go with D. So D is allowed to execute. D executes for 15 units of time, so D completes at 45. Then we have, so D is taken out from here. So here we have A, B and E. Now once D is complete, we give a chance to E. E completes its 20 units of time, that is at 65 it completes. So then E is taken out. At time instant 65, you find E completing, and again the scheduler now has to choose between A and B. The choice is with B because B is the one that is having higher priority compared to A. So B is given a chance. By the way, B had completed 5 units of time, so now it's only 10 units of time that is left for B. So B completes 10 more units of time, that is after 75 it becomes 0, and now we are left with only A. So A takes the rest of this 15 units of time. So here B, and at time t equal to 90, A completes. So this is the priority schedule that we are talking about. Okay, so we said that we can decide on the importance of processes, and depending on the priority schedule, we can build up, we can allocate processes based on their priority. But there's a problem with this priority-based schedule. And the problem is that this priority schedule may lead to the problem of starvation. We already have been introduced to this when I was talking about the burst time, the shortest job first algorithm. The same thing happens here as well. So think about a situation where the currently running processes, which are being scheduled on the basis of priority, there is a prior process, say for example in this case the process A, okay, which was having the least priority. Now for this set of processes it was okay because look at this, A first got its chance here in case of the non-preemptive one. So A got, for a preemptive shortest job, for a preemptive priority schedule, A got its chance first, And then because there were processes which were of higher priority which were coming, A was taken out. And then look at the time when A got its chance. It was after all these processes are completed, then A got a chance to execute. Now think about a situation where not only these processes, but processes they keep on coming. And all the processes which are coming are of higher priority than this process A. So that means A will be pushed further, and this will go on because A is not getting a chance because all processes that are coming are of higher priority than A. And that is the problem of starvation. When a process does not get a chance to execute. Why? Since it has the lowest priority. Okay, that is the problem. Now, how to avoid this problem? So there have been many solutions which have been proposed to avoid this problem. One can be to have a dynamic priority. So the solution to this problem would be that you cannot fix your priority a priori. That is what we were doing for the two examples that whether preemptive or non-preemptive. We were fixing up the priority, whether it was the user process or the scheduler. The priority was fixed prior to the schedule. That should not be done. Okay, it should keep the priority assignment flexible, and that is if a certain process you see it's creating trouble for another process, that is the process A, let's say, is being pushed by any one of these processes because these processes keep on coming. So you may either decrease the priority of any one of these processes so that the process with a lower priority gets a chance to execute. That can be one possibility. So decrease the priority of a process so that another process gets a chance. That can be a possibility. Or it can be the other way around. So instead of decreasing the priority of a particular process, we can elevate the priority of the lower priority process. Say, in this case, if you wish A to be executed, we can elevate the priority of a low priority process. So this can be a possible solution to this starvation problem. And this actually is done by the scheduler. So what happens is the scheduler takes the call, and what it finds is if with passage of time, if it finds that a particular process is not getting its chance, so what it does is it elevates the priority of a low priority process. And the way to do it is all processes, they start with a certain base priority, and after every time slot, say for example, if you are going for some a priority based schedule, then after a certain time the scheduler checks the priority of all the processes, and if it finds that there is certain process which is low in priority, then it keeps on incrementing the priority of these low priority processes so that they eventually at some point of time get a chance to be executed on the CPU. So that's the idea of dealing with the starvation problem. Okay, so another interesting thing that happens is we can create a priority of group of processes. So it's like this, that you have processes of different types. So these processes can be grouped into different classes. Say for example, we can have a group of processes which can be called, say, real-time process. So it's like this, that the real-time processes, okay, then there can be a group of processes which deal with system tasks. So they can be system processes dealing with the scheduler, the dispatcher, etc. These kind of system level processes that we are talking about, specifically the OS level processes. And then we can have the interactive processes, that is the more IO bound processes, okay, which require a user interaction. So they can be grouped, they can be put into a group called interactive processes. And then we can have all processes which are to be executed as a batch. We call them as batch processes. Now, if you classify processes into these groups themselves can be arranged in a priority order. So let's say it can be in this order, the priority class. So you can classify these group of processes. So you see that real-time processes are of the highest priority, then the system process, then the interactive, then the batch process. So what the scheduler does is, whenever it tries to schedule a particular process, it may first look up to this process type and find that, okay, this process belongs to this group of process, this class. Since it belongs to a higher class of process, so obviously if I have to compare between two processes of two different class, I'll take up any process from the higher class and then allocate it. Thus, preference will be given to processes belonging to the higher class. So if you have, so the one that I'm showing here is the ready queue. So what we can do is, in case a system has number of processes, so instead of having one queue, we can create multiple queues, and every queue is nothing but a particular class of process, and every queue will have its own priority class. So let's say this is ready queue number. So this is the ready queue for a real-time process. So real-time process ready queue. This is a ready queue for the system process. This is the ready queue for interactive process. So you see, you have not one but multiple ready queues. So if the scheduling has to be done between processes, say P1, P2, P3, P4, P5, P6, P7, P8, P9. If the process scheduling has to be done among these processes, P10 and P11, then the scheduler will first look up to the particular class, that is the class associated with that particular ready queue. And if the comparison has to be done between two processes of different class, so it will choose the process of a higher class. So that says if the comparison between P1 and P4, the scheduler will choose a process of higher class, in this case this ready queue process, which is P1, and will allocate it to the CPU compared to P4. Whereas if the comparison has to be between two processes of the same queue, okay, you can follow any standard scheduling technique that we have studied earlier, whether it is round robin or first come first serve or SJF, whatever it is. So there are two levels of, this is called multi-level scheduling, where you have multiple ready queues, and each ready queue has a priority class associated to that. So if the comparison is between processes belonging to two different ready queues of two different priority classes, so the scheduler chooses the process belonging to a higher priority class and allocates it to the CPU. On the contrary, if there is a choice to be made between two processes of the same class, you can go for any specific algorithm by which we can decide between the processes of the same class. So for processes within the same class, okay, we can choose the scheduling policy. The scheduling policy can be any one of them. It can be first come, first serve, or it can be round robin, whatever it is. And it can be in this way as well. So, I mean, this particular ready class chooses round robin schedule to schedule processes within this class. This may prefer FCFS. So, it's not necessary that an intra-class schedule has to be same for all classes. Okay. So, one particular ready queue may, one particular class may prefer FCFS, the other may go for round robin. Say for example, if this is interactive processes. Okay. So interactive processes, you know that these processes are of short nature time. So then they don't need to have a round robin, or it's okay to have an first come first serve. Okay. Or maybe you, if there are other classes such as batch process, you may go for round robin in this case. So that is about the multi-level scheduling. So with this, we complete our discussion on the process scheduling. We covered a number of scheduling techniques, starting with first come first serve, shortest job first, shortest remaining time first. Then we discussed about round robin scheduling. We discussed about priority based schedule, and finally we said that okay, these once you obtain a number of priority classes of, you can group processes into different class of processes, and then each one of them can have their own ready queue, and you can associate a specific priority class to each one of those ready queues. And once the particular process has been identified, there can be, if they belong to two different classes, then the one with the higher class is chosen as the one to be allocated. But if there are two processes which belong to the same class, the allocation can be using any one of the standard scheduling techniques. So that is about process scheduling. So in the next lecture, we'll be talking about some other topic. So thank you.